So here we'll talk about section 2.3. Um, we're going to start off by discussing stem and leaf plots. This section is just on other graphical representations of data. Again, even with all the stuff that we're covering in this section, there's obviously going to be more ways to represent data graphically than the ones that we talk about here. So this is not exhaustive. Stem plots are a quick and easy way to look at small samples of numerical data. You can look for any patterns or any strange data values. It's easy to compare two samples using stem plots. The first step is to they say divide each number into two parts. It maybe makes more sense saying to break the number into two parts. Here we call these parts the stem. The stem could be the leftmost digit, for instance, and the leaf. The leaf could be like the rightmost digit. There are no set rules here. You just have to look at the data and see what makes sense. So we're going to go through this process together. Here we have the percentage grades of 25 students from a statistics course. And if we want to draw a stem plot of this data, let's go through this together. It says break each number up so the tens digit is the stem and the ones digit is the leaf. So 62 becomes 6, and then we have this vertical bar, and then a 2 on the right side of this vertical bar. Then we want to make a vertical chart with all of these stems on the left side of a vertical bar, filling in any missing stems. We then want to put each leaf next to its corresponding stem. You don't have to worry about order at this step. We can always reorder the data. Let's look at this process. Let me grab a line here. Maybe I'll just need a vertical line for now. A vertical line should be sufficient. There we go. And let me swap colors here. So let's look at, I see a 40 looks to be the lowest grade in this set of grades. And I see a 95 is the highest grade. So my first stem is going to be a 4. Then, so I'm going to go ahead and say I'm going to account for this 40 here. So I'm going to cross this 40 out. And I'm going to write the 0 on the right-hand side. Let's see, are there any grades that start with a 5? We have 58. So we can write 5, and then the 8 goes over here. And then I can cross out this 58. 62 is another grade that we have here. We can mark this out from our table. 71. I'm just going through and getting something that starts with each of these stems. 81. And 95. So now from here, I just fill out the rest of the leaves. So for 87, I just write a 7 on the right-hand side of this vertical bar. For 69, I just write a 9 over here after this 2. For 87, again, I write another 7. And then I write another 2 for this next 62. And I write a 5 for the 45. We have two 6s next to the 7 for 76 and 76. Then I have a 62. Let's mark these out. Then I have 65, 67. So I write 5 and then 7. 72, 80, 77. So I write a 7 next to this 7 stem. 87. 84. 73. 93. 64. And 89 to take care of this last row of data. With this, we can redo this stem plot while reordering the data. And if we do, and also providing a nice title as well, and a legend at the top. If we do, it should look something like this. Let's compare to our stem plot here. Let's see. 2, 2, 2. We have 3 2s. They have 3 2s. 4, 5, 7, 9. Good. 7, 1, 2, 3, 6, 6, 7. Got it. It looks like everything lines up perfectly here. Awesome. So this is a stem and leaf plot. And here also, so not only do they have a title, but they have a legend up top here. So this is saying that a stem of 4 with a leaf of 0 means 40%. All right, so on top of stem plots, we're also going to look at scatter plots. So sometimes you have two different variables and you want to see if they're related in any way. A scatter plot helps you see what the relationship would look like. A scatter plot is just a plotting of ordered pairs. You just plot a whole bunch of dots. So we're being asked this question: is there any relationship between elevation and high temperature on a given day? The following data are the high temperatures at various cities on a single day and the elevation of the city. To help us establish whether there is or is not a relationship between elevation and the high temperature on a given day, we might create a scatter plot here. And if we created a scatter plot, notice on the x-axis here we have elevation starting at 3,000, which is the lowest elevation in our table. And on the y-axis we have temperature in degrees Fahrenheit. So we have the point 3,070, for instance, and 4,060, and so on for each of these data points. From this graph, it looks like there might be an approximately linear relationship here. We might be able to draw a straight line between these data points, or at least it gets pretty close to a lot of these data points. This is a pretty close fit for this data, right? This line isn't terribly far from any of these data points. I mean, and this is just by eyeballing it. This could maybe be better. I'm not 100% sure here. So as a result, it appears that there is a linear relationship between temperature and elevation. This also appears to be a negative relationship. So as elevation increases, temperature decreases. And the last type of plot that we're going to look at here are time series plots. A time series plot is a graph showing the data measurements in chronological order, the data being quantitative data. For example, a time series plot is used to show profits over the last 5 years. To create a time series plot, the time always goes on the horizontal axis, and the other variable goes on the vertical axis. Then, plot the ordered pairs and connect the dots. The purpose of a time series graph is to look for trends over time. You want to be careful because you have to realize that the trend may not continue. Just because you see an increase doesn't mean that this increase will continue forever. As an example, prior to 2007, many people noticed that housing prices were increasing. The belief at the time was that housing prices would continue to increase. But the housing bubble burst in 2007, and many houses lost value, and some have still not recovered. So the following table tracks the weight of a dieter, where the time in months is measuring how long since the person started the diet. Our goal here is make a time series plot of this data. Here, notice that months, the time, like we said, are on the x-axis. And this variable, weight, is on the y-axis. So notice that over 5 months, the weight appears to be decreasing, right? It's not a substantial decrease from month to month, but I mean, of course, like, losing 13 pounds is pretty good, right? I mean, especially because, we only have limited person data about this person anyway, right? We don't know things like how tall this person is and things like that, right? There are a number of factors that go into this kind of thing. So the last topic that we want to talk about in 2.3 is just to be careful when making graphs. If you don't start your vertical axis at 0, now it's okay not to start your horizontal axis at 0. Because, well, sometimes it makes most sense not to, such as in this scatter plot, right? It wouldn't make a whole bunch of sense to have a 0, 0 here because I don't have any data points close to 0. If your vertical axis doesn't start at 0, though, then the change can look a lot more dramatic than it actually is. As an example, the graph that we just looked at, this graph, with a different, so this graph is the last graph that we looked at with a different scaling on the vertical axis. Notice how they started the weight here at, I guess down here would have been 186, right? So the first notch here is 188 instead of starting at 0. So as a result, this decrease in weight looks very large on this left-hand graph, right? Whereas it's actually not that large whenever we look at this graph that is properly scaled. All right, and that's going to be it for section 2.3.